My name is Daniel Nenny, and I'm the founder of SemiWiki.com, the open forum for semiconductor professionals. Since going online in 2011, SemiWiki.com has experienced more than 3 million users. If you're not a member of the SemiWiki community, please register as my guest. I hope to see you there. Today's webinar is titled New Block Floating Point Arithmetic Unit for Processing AI and ML Workloads in FPGAs. The presenter today is Dr. Mike Fitton, Senior Director, Strategy and Planning at Achronix. He has more than 25 years of experience in the signal processing domain, including systems architecture, algorithm development, and semiconductors across wireless operators, network infrastructure, and most recently in machine learning. All right, this is a very interesting topic, so let's get started with a presentation, which will be followed by a question and answer session. Over to you, Mike.
Hi, everyone, and thanks to Daniel for that excellent introduction. So today, what we'll be talking about is a really interesting way of doing some machine learning processing with a new number format using block floating point that has some excellent attributes, very high precision, but also low power consumption. So we'll step through how that's applicable to FPGA. In general, I'll be using Achronix products to illustrate what we could do in this area, but the concepts are broadly applicable to any FPGA device or an embedded FPGA IP. With that, to my first slide, from an agenda perspective, we'll first talk about what block floating point is and why you might want to use it. And it's really coming back to that key concept that we've got the performance that approaches that of floating point, but with a much lower complexity than classic floating point and complexity similar to that of fixed point. We'll look at the applicability of block floating point in machine learning and in other application areas as well. Then we'll look more broadly at how FPGAs are used in machine learning. And then finally, we'll tie everything together and we'll show how block floating point can be implemented in FPGAs in general and Achronix FPGAs in particular. Now, block floating point isn't something new. It's been getting a lot of focus more recently because of machine learning, but it's actually been around for a long time as a kind of classic signal processing technique. It has most of the benefits of the high dynamic range of classic floating point, but has a much lower complexity and therefore lower power consumption, approaching that of fixed point arithmetic. The number format itself is you have a common exponent across a block of data, hence block floating point. Each of the samples has a separate mantissa, but a common exponent, which allows a lot more of their arithmetic functions to be done with fixed point arithmetic, but has the better dynamic range that you get provided by that common exponent. Classically, this has often been used in Fourier transforms, in image processing, and now is used a lot in neural networks, particularly for inference as well as in training applications. And our new Speedster7t from Achronix will be the first FPGA that natively supports block floating point. So you've always been able to implement block floating point by having the functions done in soft logic, but we natively support that in the hardened multiply accumulators. I'll provide more information on later. So let's recap number formats in general and what's the comparison of the two. So the simplest way to do any mathematical operation would be in integer or also called fixed point arithmetic. This is pretty typically used in machine learning inference as it's much more efficient than floating point. We see 16-bit numbers were classically used, but increasingly it's going to 8-bit and even less to 4-bit. So if you can accommodate not having a dynamic range, then there's a lot of benefits from a complexity point of view of using integer arithmetic. In contrast, floating point has a much better dynamic range because you have this exponent as well as having the mantissa. So the value, the exponent really is giving you the dynamic range, and mantissa is the actual value that's associated with it. We've got a few examples here. FP16 is often called half precision. That's a way of reducing the complexity somewhat compared to classic single precision float. B-float or brain float 16 is a new number format which is often used in machine learning inference, and it's just easier to calculate from a single precision floating point format. and FP24 is included here as an additional example. We support this in our Achronix Speedster7t family, but it's a proprietary format, just giving a little bit more accuracy with the same dynamic range. Now, in contrast, as we said before, what you've got with block floating point is you've got a separate mantissa, as you can see in here on the left, but there's a single exponent for this block of data. So the combination of the two gives you better dynamic range than integer arithmetic, but not the complexity that you have to have with barrel shifts and leading zero detects that you have in floating point, which adds to the complexity and adds to the power consumption in that case. Next, what I'd like to do is just step through an example of some block floating point numbers, just so you get a good idea about how this all works. So first of all, you will see we've got 4 numbers here. These are floating point numbers. They're actually bfloat16 numbers. And what we're going to do first of all is we're going to convert them into block floating point, and then we're going to do a block floating point calculation. I should stress at this point, I know it's a bit confusing. bfloat sounds similar to block floating point, but they're actually different. bfloat is a classic floating point format that's got a dedicated exponent per value. Block floating point is different than that, and I will make sure that I use the terms separately. In this example we've got here, the first thing to do is to find the largest exponent. That's this top one here that you can see. So that's the biggest exponent. So once you've identified the largest exponent in a block of data, then you find the differences from the other exponents from that largest. So you can see we have 1 position difference here and 2 in the other 2 samples that we have in the example. Second step is then to right shift the mantissa that you have, and we're going to right shift that mantissa by a value which corresponds to the difference in the exponents. So obviously the first sample will not change, but then the second sample is right shifted by 1 value. The third sample will be right shifted by 2, and you can see 2 zeros appearing in there, and the last one will also be right shifted by 2, again 2 zeros appearing in there. So now what you've got is a block floating point representation of your data coming in, of your activation. We will then take that with the red numbers that we've got here. So the red on the right-hand side is, for example, the weights. And they're either pre-calculated and pre-stored as block floating point. Storing them as block floating point obviously saves you some memory, so that's a nice thing to do. Or we could calculate them on the fly. And then what happens pretty simply is you're going to do a multiplication between your weight here in red and your activation in green. You accumulate that as a fixed point number, so you're adding the fixed point numbers together. And then with the block floating points, you simply just add the exponents. Couldn't be easier to do that. And so then you will have this as the output of these 4 values here. You're going to have your mantissa and your exponent. Then this will step into a floating point accumulator if you want to do additional accumulation going into the next cycle. So there's been a number of research studies into the use of block floating point because of the advantages associated with dense neural networks. Here I have some results from a Swiss research institute, the EPFL, but there's a number of other studies that have been done as well. So on the right-hand side, what the guys at EPFL did was they looked at FP32, so that's single precision floating point, and compared with 2 hybrid floating point number formats. What they mean is, by hybrid is you're doing the dot product that I just showed you, that's done in block floating point. The other calculations, things like activation functions, are done in floating point. So similarly, we can support it in the same kind of way. And what you can see is basically the curves are on top of each other. The training loss, the accuracy, is on the y-axis here, and on the x-axis, the epoch is the number of iterations you've gone through. The fact that the 3 different number formats are basically on top of each other in pretty much all of the cases here is showing there's little or no loss of precision in training accuracy by going to this more optimized number format. So that's a great advantage because it means we can exploit some of these nice characteristics of block floating point data. So how could we apply block floating point? There's obviously a number of different silicon devices, types of silicon devices get used in machine learning and machine learning inference. We've got everything from CPUs here as probably the most flexible. all the way to the other extreme where you've got the least flexibility in a dedicated ML ASIC, but much more efficiency. And then on the spectrum between the two, you go through GPUs and FPGAs. Now, particularly with looking at this block floating point area, it's tough to do it with GPUs and CPUs just because they tend to be optimized for single, even double precision floats, sometimes having integer arithmetic starting to be introduced there. On the other extreme, ASIC blocks give you great performance in terms of teraops per watt, performance per watt. The challenge with the ASIC is, unless you've envisaged exactly the correct number format for a new type of algorithm, you probably haven't prepared it already. So this is where field programmable gate arrays come in that the design can be reconfigured to support the particular number format that we've got. And so that gives a nice balance between efficiency and flexibility. And for new neural network algorithms, it's often FPGAs are the first to be able to implement that kind of thing, which is why we are seeing this significant growth in the use of FPGAs. So here in blue, you can see significant use of GPUs, CPUs, and ASICs. And then over the years, in this analysis that we put together at Achronix, you can see that the green portion, the revenue that's going to be spent on FPGA in this domain is increasing steadily over time. So much more, we expect to see much more use of FPGAs in the data center for machine learning inference acceleration, and also in edge compute applications as well. Now, one of the reasons why we see such applicability here is FPGAs are kind of like the Swiss Army knife of data center acceleration. They're not focused on a particular application type, but you can do multiple different things. For example, here, we're showing a data aggregation and bridging application. So classically, this is kind of the boring stuff that FPGAs do really well. It's like gluing data together. You're going to be doing bridging of different interface standards, adapting to a new interface standard coming in, be extracting data from that stream of data coming in, maybe doing some sensor fusion. That's a thing that's typically required in automotive applications where you've got different sensor types, LiDAR, radar, imaging, for example, and you need to fuse that data together before it's processed. And then in addition, you might be doing some pre-processing. For example, you might be turning it from a floating point number into a block floating point number. So all of these things are very well suited to reprogrammable logic in FPGA. But in addition to that, FPGAs also get used in the data center for doing network acceleration for things like SmartNIC and for network function virtualization. This might be things like RDMA or compression or crypto algorithms would be a different workload that could be applied as well or instead just by reprogramming the device. So you can see on the right-hand side, the PCI Express form factor FPGA that we've got is taking up multiple different personalities depending on the requirements that we have. The final area, and one you would expect me to have in here, is in machine learning inference, and particularly, perhaps less so in training. GPUs are really dominant in ML training, but where the performance per watt becomes more of a key metric in machine learning inference, especially at the edge, then FPGAs have got a really big advantage there, particularly in doing the matrix vector maths that are the key atomic operation associated with machine learning. Now, if we look at kind of classically, FPGAs for like a good 20 years now have had a dedicated multiply accumulate function implemented in ASIC. So rather than building a multiplier out of soft logic, there's a dedicated multiply accumulate function, which is great. Classically, that's been optimized for filter applications. So the typical number formats are 16-bit or 18-bit, just because that reflects the kind of dimensions that you would have coming in from an analog to digital converter. More recently, there's also been the inclusion of single precision floating point, which helps if the application is requiring a higher dynamic range, and ML training is a good application of that. The challenge with using these classic DSP blocks, they're really optimized for fur filters, and the challenge with using them in AI ML is that the number format isn't very efficient. If I can only need 4 bits or 8 bits, having an 18-bit multiplier is incredibly inefficient and very wasteful. Second of all, you need a bunch of external logic and memories to build the application itself to connect everything up. And then because everything is connected up by FPGA routing wires, then the performance is generally limited by the FPGA routing rather than any of the other functions. Now let's look side by side at the architecture of the two different things. If we look at a wireless application on the left and an AI ML application on the right, they've got, as you can tell, they've got very different data flows. The wireless application is going to have these delays up here, and then there'll be a weight applied to the data, and then a summation. So this works very well with a cascade path connecting DSP blocks, but it has relatively limited amount of memory associated with it. In the case of a machine learning inference application, the weights is quasi-static. So you'll be using the same weights again and again, or you might be using the same data again and again. And so there's also very often a systolic array implementation where the data will flow from one node to another. So as you can see, it's different, not only different data flows, it's also different number formats. And consequently, something that's optimized for a wireless application doesn't lend itself very well for an AI ML application. So let's assume you're an FPGA developer and you had a blank sheet of paper and you wanted to optimize the multiply accumulate, but for machine learning, not for wireless applications. What would you do? And as you might expect, this is a question very close to my heart, because this is exactly what we did when we were looking at our 7-nanometer family. We wanted to optimize specifically for machine learning applications and also for other matrix operations like beamforming, like radar, and a number of other wireless applications. You don't get something for nothing, and so the architecture is somewhat less efficient for FIR filters, particularly something like the architecture for a symmetric filter. You could still support it, but you would need some soft logic outside. But when you are applying to matrix multiplication, you have much, much better performance, which outweighs any disadvantages in the other area. The design includes an integrated memory that exploits the data locality I talked about a moment ago, and therefore reduces power consumption because you're not unnecessarily moving data around. The functional integration of combining the arithmetic operation, the storage, and the control reduces routing congestion, and that improves then the quality of results. It improves the Fmax that you can achieve. And the design is obviously fully configurable because you would like to support changing algorithms and new neural network types that are coming out. So diving into what's specifically included within this AI optimized machine learning processor block, it's got very dense matrix multiplication operation. So you can have up to 32 multiplies per multiply accumulate block. That would be 32 int 4 multiplies, or 16 int 8 multiplies, or 4 int 16 multiplies. In order to make it more efficient for signal processing applications, it also supports complex arithmetic as well. So that's the kind of simple mode of using integer arithmetic. We also support floating point applications as well. So bfloat16, FP16, and FP24. And that is very useful if you want the higher precision that you would get with true floating point. But then we have the block floating point that I introduced a few slides ago, which is effectively a combination of the fixed point arithmetic and the floating point accumulation. The nice thing is it really doesn't cost any additional die area because both of those functions are in there already, and it's just a different connection of using the first half of the integer adder tree and the second half of the floating point operation with the floating point accumulator, and with that you can then natively support block floating point. The next thing we have within the MLP, the machine learning processor block, is this tightly coupled memory. So it's actually configured as a separate column that's adjacent to the multiply accumulate function, and so therefore it's addressable and you can route to it completely independently. But if you want to drive the adjacent multiply accumulate from that associated memory, there's a direct connection between the two. Direct connection means you've got a higher bandwidth. The direct connection means you're not using any FPGA routing. It's going to be easier to close timing, so it becomes much more efficient. And you could use this BRAM here, 72K bits, would store a fairly sizable number of weights. So you could leave your weights in the BRAM, for example. There is also a register file that can be used for example, if you wanted to do some time multiplexing. So you could time multiplex inputs or time multiplex outputs and store them in the register file just to add more flexibility, and again, without having to use any of the FPGA soft logic resources for that kind of thing. The next part of the function is how these blocks are connected together. So there's a cascade that goes up and down the column to cascade the memory. So I would use the memory cascade, for example, if I wanted to form a larger memory than 72K bits. If I wanted 144K bits, I would then just cascade two of the memories together. I can also cascade either of the operands into the multiply accumulate. This is really nice if I've got the weights stored here, for example, then I can keep my weights locally. I can cascade the data value up, and I can form a systolic array type implementation by just cascading all the data up, again, without stepping out of the column, because you are immediately directly connecting from one of these MLP blocks to the adjacent MLP, either up the column or down the column. Now, how this looks overall, specifically in the case of block floating point, I know this is kind of an eye chart, but if you look on the left-hand side, you've got a pretty simple fixed point adder tree over here. So you've got your two operands coming in each of the cases, and each of your values that you've got, where you've got 8 multiplications here that are being summed together, a second stage in the adder tree, and everything of your 8 calculations are all being summed together. So this is a classic fixed point adder tree that we've got here. The new part is you've got these 2 exponents coming in. So for 2 exponents for your 2 different operands. And then simply by summing them together, after some registers have been included as pipelining stages to balance the pipelining, you then have this exponent to then go into this floating point FP24 accumulation. So that's then the second part on the right-hand side, which is doing the accumulation of the value. And each of the new values coming in here will have a mantissa associated with the result, but an exponent which is simply a sum of the 2 operand exponents. And then that will get summed with the accumulated value that you've got. The values are natively accumulated as FP24, but they can be cast to be FP16 or bfloat16 on the output. So you get a lot of flexibility in terms of how everything is used like that. So we kind of started in the detail about what does the block look like, but in terms of the compute processing that we've got here, the compute processing is kind of useless if you can't feed the beast, if you can't get data to this high performance block we're talking about. So we did a lot of close architectural study in our Speedster7t family that is built on TSMC 7 nanometer to not only have high performance compute, but also to balance that with high performance data transfer and high performance memory bandwidth. Now, the data transfer is supported by really high bandwidth coming in. So up to 72 lanes at 112 gigs on the largest family member that we have, but also supporting multiple hard IPs for the PCI Express Gen 5 and 4x400 gig Ethernet. And this is true 400 gig Ethernet with 4x100 gig. So Achronix will be the first FPGA to support 4x100 gig, 4x100 gig to give 400 gig Ethernet, and first to support PCIe Gen 5. The other key part that we've got is this network on chip, and you'll start to see over the next couple of slides how important this is. The challenge that we have this generation is, if you look this generation compared to the last one, we've got about twice the logic resources in new FPGAs. This isn't just Achronix, this is pretty much any FPGA provider. We've about double the density we've supported, but we've increased by more like a factor of 10 the data coming in. So if you're not careful, you end up using your FPGA resources just moving data around. So what we instituted was a network on chip that both connects up the external parts in the periphery, so it allows you to write from PCI Express Gen 5, for example, directly out to GDDR6 without coming into the fabric, but also a network on chip that permeates into the fabric. You've got these multiple pipes, which are each 512 gigs, so 256-bit wide at 2 gigahertz. and that moves data in and around the chip. The benefit with that is you're not using your precious soft logic resources to connect stuff up. You're using all of that soft logic to do useful processing. And from experience, oftentimes in classic FPGA designs, you can have more than half of your logic just used to pipe stuff up, to plumb everything together. So in this case, all of those resources are offloaded into the hard network on chip, and you have much more resources available to you for doing useful processing instead. And then the final part that we have on this device is this high memory bandwidth, 4 terabits per second, but using GDDR6, not HBM2. We made a conscious decision to pick GDDR6 mainly because it has the lowest system cost. GDDR6 devices are generally being driven down to a lower cost than HBM2 memories, and lower system cost is obviously important when we're considering a machine learning inference application. So really high memory bandwidth, really high network on chip bandwidth to move the data around, lots of big fat pipes to get data onto and off of the chip, and then the new machine learning processor to consume all of that data and do something with it. So once we tie all these things together, what you end up with is some pretty significant performance. So we've got the performance here in teraops. Now, and we'll demonstrate in a moment, teraops isn't always a great example of usage. You really need to think about what's your useful teraops. How many can you actually load? But people often use teraops as a comparison point. And so we'll do like the headline figures that you'll see here. And you can see that at 61.4 teraops of int8, that's the highest FPGA multiply accumulate block of any FPGA that's publicly announced on the market at the moment. So any of the devices from us or from Xilinx or from Intel, this is the highest performance for int8, and int8 obviously being a great application for machine learning inference. Similarly, you can see exactly the same number, 61.4 teraops of performance. So kind of the block floating point is kind of coming for free. You've got the same performance as int8, and you've got this common exponent giving you a better dynamic range. And if we compare back to FP16, you have 8x performance in comparison with that. So a real performance boost that you get by using block floating point in this example. And as I stated previously, we have the only FPGA that's natively supporting block floating point. You can use it in other FPGAs, but you would need to use soft logic that surrounds it. Using soft logic consumes resources, and it drives down the performance that you can achieve as well. Now, if we talk about that, that also comes into the power aspect of things as well. Natively supporting block floating point means that our devices inherently are going to be lower power when supporting this mode. If we compare the int8 performance now with block floating point, you can see a modest increase in the power, 15% higher power, exactly the same number of tops, if you remember from the previous slide. So there is a cost with that extra dynamic range, but it's minimal compared to what's supported, and you get some significant benefits associated with that. So some big benefits with all these things, but how do you implement it at scale? And this comes back to the point I said about earlier on that raw tops aren't always a useful measure. What you really need is effective tops. So what we have here, this is actually the output from our software tools of a floor plan design. And each of the kind of squiggly blobs that you can see is a conv2D reference design. So it's actually going from, it's a very nice regular structure because it's going from network access point, so a NOC access point at the top is the ingress, and then the egress at the bottom of that. And what we've done is connected up a significant number of the multipliers, so 94% of the multipliers, talking with 94% of the memories. So they're all combined within that machine learning processor that we talked about. But because you didn't have to use any logic or routing to connect everything up, we're only using 4% of the logic to connect all of this. So the great thing about that is that logic is then available for you to do something else. You can do your activation data if you wanted. You can use that logic to create some more multipliers. You can do it to use whatever else you wanted. And the fact that we're also closing timing at 750 megahertz means that you can have excellent performance out of this as well. So this is, I think, is a really nice example of where the network on chip is definitely giving some benefit. Having 750 megahertz of performance in the core is great, and so it makes it much easier from a time enclosure point of view. You, as a user, you don't have to worry about time enclosure. It's easier to instantiate a NOC access point and then just connect to that. And then in terms of modular design, you can see it's very regional in terms of design, so that makes it much better for hierarchical designs and things like partial reconfiguration, and therefore gives you a much better time to market in this space. And then let's just tie it all together. Remember I said 61.4 tops was the maximum number. In this design, real design we've got here, we are achieving 57.7 of those 61 tops. So really a high performance is coming out of this as well. So I think this is a great example about how we can deploy at scale with these large devices. So just to try and summarize and put things into context for you all, we see that FPGAs are great at providing this reprogrammable, flexible workload accelerator for edge compute. That could be data interfacing, remember that we talked about, could be pre-processing, but it can also be the machine learning inference engine itself. So there's a significant applicability of that flexible processing that you can do in the FPGA. It is possible, we've demonstrated it's possible to tune the FPGA architecture for the requirements of machine learning. So that's the three different aspects we talked about: data compute, data moving that data around with data transfers, and storing that data in a memory hierarchy. Only by doing those three can you maximize those usable tops that I talked about as well. And from an Achronix point of view, we support this FPGA fabric both as our Speedster7t standalone FPGAs that we will provide as individual devices and also on PCIe acceleration cards. But we also have an embedded FPGA that means that you could license this exact same fabric to cost reduce an FPGA or to integrate it in with an ASIC and SoC. And so then it enables multiple different deployment models everywhere from the data center through to edge compute. So that's the end of everything that we wanted to talk about. Just before we open things up for questions, I do want to give a brief brief shout out to the other content that Achronix has got on. We love working with semiwiki.com, and they have a page dedicated to some of the Achronix content, and I encourage you to get in touch with us or to check out our other content on SemiWiki. And with that, I'm going to hand back to Daniel.
Thank you, Mike. Well done. All right, let's get the questions and answers session started. In case we don't have time, if you submit a question, we will respond to you via email. All right, first question, Mike. What applications benefit the most from block floating point?
Yeah, thanks for the question, Daniel. So there's a pretty wide set of applications that benefit from this. Obviously, I talk most about machine learning, and that's an obvious example of that, because either your activation or your weights tend to be grouped in a similar dynamic range, but other types of calculations are similar to that, or they need to have some bit growth accommodated. FFTs is a good example of that. With an FFT, each stage of an FFT you step through, classically you would have, if you were using fixed point arithmetic, you'd have to grow your fixed point number by a single bit. But if you've got a block floating point number, you don't need to do that. So it's a more efficient way of doing something like an FFT. Similarly, I've seen it used a lot in matrix mathematics, things for matrix multiplication, matrix decomposition, where the dynamic range becomes really important. Then something like a block floating point representation is a really nice trade-off between the performance of a floating point, but the lower complexity of fixed point numbers.
Great. Next question. How does a GPU or CPU compare to FPGAs when implementing block floating point math?
So we see GPUs and CPUs being used very extensively, particularly in the machine learning training part, rather than necessarily machine learning inference. So when you're calculating the weights for the neural network the first time around, they tend to have single precision floating point, maybe even double precision floating point, but they don't necessarily have a block floating point being implemented. they're not as well suited to block floating point because, as soon as you've done it in a GPU or CPU or even an ASIC, you've kind of made a choice about what your number format will be, whereas it's difficult to do that. Sometimes your mantissa will need to be a different size or your exponent will be a different size. And so that's where FPGAs in general really come into their own in that kind of application where you need a lot more flexibility.
Okay. Next question. How do you configure the machine learning processor to operate in fixed floating or block floating point?
Yeah, so we try and make it as easy as possible for you guys to do this. You don't have to write any special RTL on this, and we're going to provide a bunch of library functions for the kind of common operations you expect to see in machine learning and other applications. So things like conv1D, conv2D. So we will provide those examples, but we'll provide them in a clear text format so you can see the low level of how the block is instantiated. And really the MLP is just instantiated like any other DSP block you might do from any FPGA. You're configuring the modes of operation, and then automatically, as you've configured those modes of operation, that gets extracted by our ACE software, and that does the rest. That provides the bit stream that then programs the device to have whatever characteristics you desire.
Okay. Another question. How does the Speedster7t with machine learning processors compare to other FPGAs with DSP blocks?
Yeah, that's a good question. So I think it's a really interesting time for FPGAs at the moment, partly because everyone's gone in kind of a different direction. So I have tremendous respect for our competitors at Xilinx and at Intel PSG. Xilinx, to start off with, they go a really interesting direction with heterogeneous multi-core. So rather than focusing on the FPGA optimization, they're going new different cores. So they've got ARM CPUs and they've got GPUs and they've got these new vector engines, they're AI engines. That means that you can get lots of performance out of their AI engine. That's a different approach than what we've taken. We've focused on optimizing the FPGA rather than putting a new block in next to it. There's advantages and disadvantages of both, and I'm sure we'll just see which is more successful in the market. And they have different application areas as well. So that'll be a really interesting comparison. The comparison with Intel PSG, so Intel FPGAs, it seems like the Intel FPGA in their latest incarnation has gone much more focused on floating point, specifically on single precision floating point. My assumption is that that's because they're targeting machine learning training applications where you use single precision floating point or other applications. And I assume partly because they've got so many other solutions that they can target for machine learning inference. There's obviously DL Boost, which is integrated in the Xeon. There's the Nirvana and then the recent Habana acquisition as well, all focused on ML inference. So they have a surfeit of different choices. So yeah, in comparison, we've really focused on optimizing the FPGA fabric for machine learning inference rather than putting in a multi-core or putting in a different device like our competitors have. Another area where we differentiate somewhat is we're unique in providing standalone FPGAs and also licensing the FPGA fabric as an IP core. And we feel this is the best to disrupt the market and to enable a bunch of different usage models. It makes it really exciting as you can start to see FPGA being deployed everywhere from the cloud all the way right to the edge where it might be a small region of FPGA IP integrated with another function. And we feel that enabling that is really positive for the industry as a whole. But as an excellent question, and like I said, I think we've got really exciting times ahead for the whole FPGA industry, lots of innovation and lots of different strategies. So it'll be interesting to see who's the most successful.
Yeah, I agree. It is an exciting time. We have one more question, and maybe this is more of a general question, but can you provide some more background on the NOC?
Yeah, that would be great. We've got, I think there's even a webinar on this topic as well. NOCs are relatively new in this generation of FPGAs. Xilinx has got one. I would encourage you to go and look at what they have there. They're more focused on the connection of the connectivity. We have something similar, but we also have the connection into the FPGA fabric itself as well. The one around the periphery, from our point of view, is relatively conventional NOC that allows you to come in, for example, I think I said in the presentation, come in on PCI Express to talk directly to a memory, DDR4 or GDDR6 memory, witithout having to go to the fabric at all, and without even having to write a single line of RTL. So that's a nice feature in terms of productivity and offloading resources. Where I think the innovation really steps up, though, is the fact that that NOC also permeates the fabric. It doesn't divide up the fabric, but it's like having an overlay, like a series of freeways that run over the city streets, and then you've got an off-ramp or an on-ramp that takes you to a NOC access point. And so those higher bandwidth connections that fly over the FPGA are really good at kind of bringing the data to where you want to do the processing. The challenge with classic FPGA design in this is it's a little bit like getting that freeway and bringing it downtown and terminating at a stoplight. You've got 400 gigs of Ethernet data, for example. That's you need to run your fabric at 724 megahertz, 1024 bits wide. That's really like a stoplight at the end of a freeway if you're not careful. Whereas having the NOC means you can drop it to the region where you want to be doing the processing. So we see big benefits in ML applications, but also in things like networking applications with 400 gig Ethernet as well. And then obviously from a tools point of view, we're supporting that through our ACE design software in terms of the usage model of how you instantiate the NOC and the arbitration that's automatically set up with that as well. But yeah, I think it's really interesting architecture. We're very proud of what we've done in that area, and I fully encourage the participants to ask us any other questions on that, or check out the stuff on SemiWiki or Achronix.com.
Okay, that's all we have time for today. Thank you, Mike, and thank you everybody else for tuning in. Have a good day.